In the first presentation on mechanics, we will introduce the basic ideas and concepts in the theory of motion called kinematics. The content of this presentation is the following. Starting with the basic definitions related to mechanics, we will give some historical introduction providing an orientation to this topics. Then we will introduce the concept of the frame of reference, which is necessary to describe the motion of any object or body in the space. Since the application of coordinate systems allows us to give a quantitative description of motion, we will present the most frequently used coordinate systems in mechanics. When we talk about the motion of bodies, we also introduce some idealized models of the moving objects, such as the point mass, systems of point masses, and rigid or elastic bodies. Then we introduce the basic kinematic quantities which describe the momentarily location of bodies, the speed and the direction of their motion, and even the change in the speed and direction as a function of time. We also express the kinematic quantities in different coordinate systems, so that we can study the nature of different types of motion in mathematical form. If the kinematic quantities of the moving bodies are given as functions of time, these functions are called equations of motion. The main goal of kinematics is to determine and study the equations of motion of bodies approximated with idealized models. Then we finish this presentation with the moving frames used in kinematics. This concept refers to a formalism based on a set of vectors characterizing the shape of the trajectory of any moving body. We call this set of vectors as a frame, which is attached to an arbitrary moving body and provides the convenient description of the kinematic quantities in this moving frame. This lecture is about kinematics, which is the study of motion in nature without concerning its cause. Since kinematics is one of the branches of mechanics, we need to introduce some scientific concepts of mechanics defined in the terms of everyday ideas. Mechanics is the study of the simplest form of the motion of bodies. In this statement we need to determine the concepts of motion and bodies from the viewpoint of mechanics. Let us start with the concept of bodies in mechanics. Bodies are macroscopic systems which consist of a great number of atoms or molecules, and their sizes are orders of magnitude greater than the distances between their constituent particles. This definition holds for any object or body which can be found in our everyday environment. Such a body is, for example, a ball we can throw or kick. Or somewhat a more complicated body, like the pendulum clock with its swinging pendulum and rotating hands. Another group of moving bodies are the vehicles, such as bicycles or trucks. However, in mechanics we do not restrict our attention to the bodies in our direct environment. We can leave the surface of Earth, and study the motion of spacecrafts or even the rotation of Earth and its orbits around the Sun. But we do not stop at the vicinity of Earth. We can also examine the motion of other planets in the solar system or the motion of the matter in galactic or supergalactic scales, where the principles of mechanics can still be applied with some reasonable approximation. From these examples it is already clear what a versatile family of objects can be considered to be bodies in mechanics. Now we determine what we call motion in mechanics. The mechanical motion is the change in the spatial location of the bodies or their parts with respect to each other. This simple definition can be easily demonstrated in the following examples. In the first example we see the snapshots of a bowling ball thrown toward the pins. The sequence of shots indicates that the ball can be found in different locations in the consecutive instants of time. If we connect the locations of the ball in the photo we obtain its path or trajectory along which it moves. Another example is the photo with a bullet going through an apple in slow motion. Although we cannot see the path of the bullet, the impact of the projectile is evident as it is crashing the apple. The next picture shows how we can follow the fall of the domino tiles from moment to moment, where the motion is always restricted only to a couple of tiles but it propagates through the row of tiles in time. A well-known example of the slow-motion photography is the capture of the traffic in the evening, where the light trails of the cars indicate the trajectories of their motions on the highway. The last example is just a spinning top where the spinning motion is demonstrated by the orientation of the axis of the top, as only its point touches the ground on which it is spinning. All these examples of moving bodies can demonstrate what kind of phenomena are studied in mechanics and kinematics. Let us start with a brief introduction on the history of those ideas and concepts which shaped the development of kinematics. The word kinematics was introduced by André-Marie Ampère, one of the founders of the theory of electromagnetism. He used the word kinema, which means movement or motion in Greek, and created the word kinematics with the meaning of the science or study of motion. The basic concepts in the study of motion already appeared in the ancient Greek thinking. The Ionian philosophers extensively studied natural phenomena and tried to provide some reasonable explanation of the motion and change in nature. However, the Ionian physics described natural phenomena as different qualities or elements mixing with or changing into each other, which was a qualitative description of motion and change rather than a quantitative one. We can consider the Greek atomists, with their two founders Leucippus and Democritus, as the first thinkers who provided a more quantitative picture on motion and change in nature. They claim that the two basic constituents of the cosmos are atoms, which are tiny material particles indiscernible with human senses, and the void, in which the atoms exist. In their view, atoms have intrinsic quantities, which are the typical properties of material object, such as shape and size, but they also considered motion as such an intrinsic quantity. According to the atomists, these atoms fall through the void with the same speed because of their own weight, but this motion is random, therefore atoms collide and bounce off each other during their fall. This shows that the atomists already applied some basic notions and concepts of physics and mathematics to describe motion, but they did not have any systematic study of this phenomenon. Plato had also some comments on motion in his dialogues, but he discussed it in a general form partially based on the atomist and the Pythagorean teachings. The first, very detailed and systematic study of motion appeared in the Aristotelian physics. Based on his geocentric cosmological concepts, Aristotle stated that the laws of motion are different in the celestial realm, that is in the heaven, and in the sublunary sphere, that is in the region below the moon. Applying the geometric principles inherited from the Pythagoreans and Plato, he considered the circle as a perfect shape. Therefore, the uniform circular motion of the stars and planets indicates the divine nature of the celestial spheres. In his view, the nature of the motion in sublunary sphere is completely different from the one in the celestial spheres. Aristotle applied physical principles to describe the motion there, claiming that the bodies rise or fall with different speed according to the ratio of the elements of which they are composed. He called such a motion natural motion, indicating the objects move to their natural positions in the sublunary sphere. In that sense, the state of rest is also the natural state to which all things return. In the case of unnatural motion, external effects act on bodies, moving them in some direction. In his analysis of the natural and unnatural motion, Aristotle used mostly qualitative explanations with concepts such as direction or speed, which formed the basic notions in kinematics. Let us leave the ancient times now and continue the history of kinematics from the Renaissance era, which was the cradle of modernity. We may consider Galileo Galilei, an outstanding scientist lived during the Renaissance in Italy, as the first physicist in the modern sense. His scientific innovations were essential to understanding the laws of nature. Since in his view the laws of motion are the same for the entire universe, there are no separated celestial realm and sublunary sphere, but the same physics prevails both in heaven and earth. This concept was inherited from Giordano Bruno and Copernicus. Galilei introduced the mathematical definitions of the basic kinematic quantities such as the distance, the velocity, and the acceleration. As a consequence of his definitions applied in kinematics, the description of motion can only be described with respect to an observer. That is, motion is relative. By using the basic kinematic quantities, he was able to give a strict quantitative analysis of motion, based on mathematical and geometrical principles. What also makes him a physicist in the modern sense is that his quantitative analysis of motion is based not only on theory but also on experiments. On the one hand, Galilei laid down the mathematical formalism to describe this phenomenon, but on the other hand he always carried out many experiments in a systemic way to study the different types of motion and gather empirical data on the course of them. The next crucial stage in the history of kinematics is related to the contribution of René Descartes to the theory of motion. Descartes was the first who applied the general principles of coordinate geometry in the quantitative analysis of kinematics. He also introduced the rectilinear coordinate system to solve geometrical problems, which turned to be extremely useful in the description of motion. This coordinate system is also called Cartesian coordinate system, and according to an anecdote, Descartes invented it when he was staying in bed until late. He was just watching a fly on the ceiling from his bed and pondering on the best way to describe the location of the fly. Then he came up with the idea that the corners of the ceiling could be used as reference points. When he studied the nature of space, bodies, and motion, he attempted to reduce laws of nature to kinematics by applying the principles of geometry and arithmetic. The last scientist we mention here is Isaac Newton, who is considered the grounding father of the modern physics. His greatest achievement was the development of the universal laws of motion. We can remember the anecdote about the falling apple, which led him to the discovery of theory of gravity. In his first law of motion he introduced the concept of the frame of reference related to the observer of the motion. This law also claims that motion is relative. Newton also stated in his laws of motion that the uniform linear motion is the most natural way of motion since no external effects are present, as opposed to the Aristotelian claim on the state of rest being the most natural state. His scientific results are based on both his universal theory and the experiments he carried out to test the theory. We may also mention that Newton was the first who applied the polar coordinates to describe the positions of individual points in the plane, although they were invented in the ancient times by Hipparchus to describe plane curves. After the introduction about the history of the basic ideas in kinematics, let us start with the concept of the frame of reference used to study the motion of bodies in nature. The position and the change of the position, that is the motion of any material body, can only be described with respect to other bodies. In this figure a moving red ball is shown, where its motion is indicated with the green arrow. This motion is observed with respect to a group of other bodies, for example a cube, a cylinder, and a sphere, where the positions of these solids do not change with respect to each other. When the ball is moving, it is changing its position compared to those of the other bodies, and this motion can only be described with respect to them or to another arbitrary group of bodies. That means the motion is always relative. If we want to describe the motion of any object, then we have to choose other objects as reference bodies, and compare the instantaneous position of the moving body to the positions of the reference bodies. The number of the reference objects is arbitrary, provided that they do not change their spatial positions with respect to each other. In most cases it is enough to choose only one reference object, but we're talking about the general case, when more bodies are singled out as reference objects. We call this group of objects the frame of reference. In this example the group of the cube, the cylinder and the sphere was chosen as the frame of reference to describe the motion of the red ball. The frame of reference can also be the laboratory where we carry out our experiments on the motion of bodies, a vehicle moving on or in the vicinity of the Earth, or the Earth herself, or any system of the fixed stars in the sky. Thus the choice of using any set of objects as a frame of reference is arbitrary, but it is practical to choose such a set of objects which allows us to have the simplest possible description of the motion we study. Let us discuss the concept of the frame of reference in more detail. The frame of reference must always be given, since the same motion of a body may be completely different with respect to different frames of reference. For example, with respect to the frame of a moving bicycle its pedal is running along a circle, but with respect to the road, its motion is described with a cycloid. Here the paths or trajectories of the moving pedal are given by two completely different curves, which shows how essential a unique frame of reference is in the description of the motion. If we want to describe the position of a body with respect to a given frame of reference, then we need to define some points, lines or surfaces, that is a set of geometrical elements attached to the frame of reference. Then we can measure the distance of these elements from the given body, which uniquely determines the location of the moving body in space with respect to the reference frame. If we attach more points to the object chosen as a frame of reference, as in this figure, then the instantaneous position of the moving ball can be uniquely determined by its distances from the points. We can also use lines oriented along the edges of the object and measure the minimal distances of the moving ball from these lines. This method gives the unique position of the ball as well. Planes can also be attached to the surface of the object. Then the minimal distances of these planes from the ball provide its unique position with respect to the object. We normally use some combination of different geometrical elements attached to the frame of the reference, and we measure the distance of the body from these elements. Now we are ready to introduce the concept of the coordinate system. The set of the geometrical elements used to determine the position of any point in space is called a coordinate system. Then the measured distances between the point and these elements are called the coordinates of the point in the given coordinate system. We can have a quantitative description of the position of a body in space if we attach a coordinate system to the frame of reference. The position of the body is uniquely determined if the number of coordinates is equal to the dimensions of the space in which we use the coordinate system. When we study the motion along a line, it is enough to apply a one-dimensional coordinate system. Such a coordinate system consists of the reference point O, called origin, and a line with orientation called x-axis, both located on the path of motion. One coordinate, called x-coordinate, is enough to determine the position of a moving body along the line, which is the distance between the position of the body and the origin O. In the case of the planar motion, we need to use a two-dimensional coordinate system. For a circular motion, we can attach a polar coordinate system to the center O of the circle, which we consider as the reference point. Then the position of a body moving along the circle is determined the two polar coordinates. The first one is the distance of the body from the point O, that is the radius r of the circular path. The second one is the angle phi measured between the position of the body on the circle and an arbitrary axis through the center O. The value of an arbitrary angle can be determined by distance measurement, that is measuring arc lengths along a circle with unit radius. Then we can always talk about distance measurements in a general sense. For spatial motions, we need to apply three-dimensional coordinate systems, where three coordinates determine the position of a body in space. The most popular coordinate systems in mechanics are constructed by applying an orthogonal set of three axes. We will use three of these types of coordinate systems. The first one is the Cartesian or rectilinear coordinate system with the Cartesian coordinates x, y and z. The second one is the cylindrical coordinate system with the cylindrical coordinates ρ, phi and z. The last one is the spherical polar coordinate system with the spherical polar coordinates r, theta, and phi. In all the three cases we use three coordinates, which are distances or angles describing the position of the point P with respect to the origin and the axes of the coordinate systems. We can use coordinate transformations between these coordinate systems, provided their origins coincide and their axes have the same orientation. If it is not the case, we need to apply space translations and rotations together with the coordinate transformations. Then we have a composition of the coordinate transformations and the space translations and rotations. If the coordinates of a point are given in one of these coordinate systems, then they can be transformed into the coordinates given in any of the other two coordinate systems. Therefore, they provide an equivalent description of the position of any point. If the coordinates x, y and z of the point P are given in the Cartesian coordinate system, this coordinate transformation maps the Cartesian coordinates into the coordinates ρ, phi and z of the cylindrical coordinate system. The inverse of this transformation sends the cylindrical coordinates into the Cartesian ones. We note that some curvilinear coordinate systems have a point set where the coordinates are undetermined. These points are called coordinate singularities. In the case of the cylindrical coordinate system, the z-axis is undetermined for the azimuthal angle phi. This indeterminacy is indicated in the equation of the angle phi expressed as the arctangent of the ratio of coordinate x to the coordinate y. Both x and y vanish along the z-axis, and their fraction gives 0/0, which is undetermined. This pathological property indicates that at the singular points, the cylindrical coordinates need to be transformed into the coordinates of other well-behaving coordinate systems, for example into the rectilinear one. The Cartesian coordinates can also be transformed into the coordinates r, theta and phi of the spherical polar coordinate system. This coordinate transformation has also an inverse which maps the spherical polar coordinates into the Cartesian ones. We can also find coordinate singularities in the spherical polar coordinate system. Such a singular point is the origin O where the coordinate r vanishes. Then the angles theta and phi are undetermined in that point. The equations expressing the angles theta and phi as functions of the Cartesian coordinates indicate this indeterminacy, since the fractions in these equations give 0/0. Two other point sets of singularity are the north and the south poles of the unit sphere around the origin O, determined by theta equals 0 degrees and theta equals 180 degrees, respectively. On both poles the longitudinal angle phi is undetermined. These coordinate singularities can also be covered with the Cartesian coordinate system. There are also coordinate transformations between the spherical polar and the cylindrical coordinate systems. This transformation maps the spherical coordinates r, theta and phi into the cylindrical coordinates ρ, phi and z. And its inverse transform sends the cylindrical coordinates into the spherical polar ones. Here we also need to stress that there is a clear distinction between frames of references and coordinate systems. If we pick up a frame of reference, we can attach an arbitrary number of coordinate systems to it. Here we use two of them with the same origin and orientation. Then we can apply any of the coordinate systems to determine the position of a moving body with respect to the frame of reference. We only need to use coordinate transformations between these coordinate systems to describe the position of the body in another coordinate system. But if we have more than one frames of reference, we normally attach a different coordinate system to each of them. Let us consider two frames of reference, where the second frame is moving with a constant speed in a given direction with respect to the first one. Now we can endow both of the frames with coordinate systems. In this case, we need to transform the kinematic quantities of a moving body with respect to one reference frame to those with respect to the other reference frame with space and time translations and spatial rotations, which are called Galilean transformations. Then it is not enough to use only coordinate transformations between the two coordinate systems attached to the different frames, but we also have to apply the Galilean transformations. As a result, we have composite transformations made of these two different sets of transformations, which shows that the frame of reference and the coordinate system are two different concepts. In order to give a comprehensive description of the moving bodies, we need to talk about all their relevant properties for the study of their motion. The strict description of real bodies is generally a complicated task. However, in many cases the size of the given body is negligible to the characteristic distances related to its motion. For example, in the case of a falling ball, or the Earth revolving around the Sun. In such cases we can consider the body as a point-like object. This means we neglect the spatial extension, that is size or the shape of the object, but we still take the mass of the body into account. As a result, we consider a given body as a point mass or a point-like particle with a given mass. The point mass has no spatial extension but possesses mass, that is, the mass of the body is concentrated in a single geometrical point. This is the simplest idealized model, which can be used to replace the real bodies in the study of motion. In the examples we mentioned earlier, we can replace the ball with a point mass concentrated in its center with the mass of the ball, and we can also use a point mass instead of the Earth if it has the same mass and is located in the center of Earth. Besides this simple model, we need to use more complicated ones for a more accurate description of moving bodies. Such a model is called a rigid body. In some cases the point mass model gives only a crude approximation. For example, the shape of a projectile is important, since the resistance of the air has a considerable effect on its trajectory. The point mass model cannot either be applied in the study of the rotation of a body around its axis, where the spatial extension of the body is crucial. In such cases we need to take into consideration the extension and the shape of the body. If we take the extension, size or shape of the body into account, in some cases we can still ignore the motion of the different parts of the body with respect to each other. The motion or the displacement of the different parts of a body is called deformation, which is a process where the size and the shape of a body is changing. If we neglect the deformation, we can introduce another idealized model called rigid body, where the points in the object cannot change their positions with respect to each other. The model of rigid bodies can be applied in the study of a broad class of phenomena in mechanics, provided no phase transition takes place in the process. There are several ways to classify the phenomena studied in mechanics. Based on the nature of bodies approximated with idealized models, mechanics can be divided into the following topics or areas. Mechanics of a mass point. Mechanics of systems of mass points. Mechanics of rigid bodies. And continuum mechanics for solid bodies, which covers elasticity and plasticity. By following another approach based on the description of motion, we can split mechanics into kinematics and dynamics. Kinematics is the theory of motion, and only describes the motion of bodies without studying the cause of their motion. Dynamics or kinetics is the theory of forces, where we take any phenomena into account which have effect on the motion, and where we also study the interactions between bodies. A special case of dynamics is statics, which is the study of the forces without motion. In statics we examine bodies in the state of rest, and determine the criteria for their balance. In order to study kinematics, we need some basic mathematical and geometrical notions related to the quantities which can describe the motion of the point-like bodies. These notions are the scalar and the vector. Those physical quantities, which are completely determined by a numeric value and a physical unit, can be described with scalars. Typical examples are the time measured between two events, let's say 10 seconds, and the volume of a body, let's say 100 cubic centimeters. But in kinematics we also need another type of quantity, called vector. We define the motion of a point-like body as its displacement or the change in its position. For a ball moving from a given position to another one, we can use the point mass model, where we identify the position of point mass with the center of the ball. When we talk about the motion of a body we have two things in mind. How much is the distance between the initial position O and the final position P of the moving body? And in which direction has the body moved, That is, what is the direction of the line connecting the initial position O and the final position P. Then the motion can be described with a directed straight segment. Its graphical representation is an arrow pointing from the initial position O to the final position P, and its notation is given by the letters OP with an arrow over them. We call this directed straight segment the displacement of the body. The length of the directed straight segment OP is equal to the distance between the starting and end points of the motion. And the direction of the segment gives the direction of the motion, that is the direction of the line connecting the points O and P. This segment is completely determined by the relative positions of the points O and P. As a result, the location of the starting point of a displacement is irrelevant. What matters is the relative positions of the starting and the end points. In the case of two or more displacements of a body, we can construct its net displacement. The composition of the displacements is based on the parallelogram law. If there are two different displacements with the starting point O and the end points P1 and P2, we can proceed as follows. First, we construct the displacement starting the point P2, which is parallel with the displacement OP1. Let's denote this displacement with P2P, directed to the point P. Then we construct the displacement from P1, which is parallel with the displacement OP1. This displacement also ends at the point P and it is denoted with P1P. Now there are two ways to reach the point P from the point O with these displacement vectors. In the first way, we move along the displacement OP1. And then along the displacement P1P, which is equivalent to the displacement OP. In the second way, we take the route along the displacement OP2. And then along the displacement P2P, which also gives the net displacement OP. Then the parallelogram law states the following. The net displacement OP of the two displacements OP1 and OP2 is given by the diagonal OP of a parallelogram constructed from these displacements. Now we can define vectors as such directed straight segments or displacements, which can be constructed by using the parallelogram law. Here the displacement OP is a vector. Furthermore, we can find such displacements which can be used to construct the displacements OP1 and OP2 as well. This shows that OP1 and OP2 are also vectors, and we can conclude that any general spatial displacement is a vector. However, not every directed straight segment is a vector. For example, the rotation axes of spatial rotations are also represented with such segments, where the length and the direction of the segment indicate the rotation angle and the direction of the rotation axis. But the composition of such rotations is not commutative, that is, they don't obey the parallelogram law. Then the oriented rotation axes cannot be considered vectors. Just as a reminder, let us have a brief overview on the basic vector operations. First of all, we note that two vectors are equal if they have the same length and direction. That is, if we have the vectors A and B, then the arrows A and B with the same length and direction indicate that the two vectors are equal. The boldface type will be used as the vector notation throughout this lecture. Here we have an equation stating that vector A is equal to the vector B, which is a vector equation and combines two statements in one equation. The first statement is that the length of the vector A is equal to the length of the vector B. The length or the magnitude of a vector is simply denoted with the letter of the vector without using the boldface type, or it can also be denoted with double vertical bars, similar to the notation of the absolute value of a number. The second statement of the vector equation is that the vectors A and B have the same direction. That is, they are parallel and have the same orientation. This means if we have two vectors, let's say A and C, and if they have either different lengths or different directions, then they are not equal. Here we see that the vector C has the same length as the vector A, but it points into a different direction. Therefore, the vectors A and B are not equal. The first vector operation presented here is the sum of two vectors, which is called resultant, and is defined by the parallelogram law. If we have two vectors A and B, which point in different directions, we can just take the first vector and translate the tail of the vectors to the tail of the other one. Then we construct a parallelogram from the vectors. The diagonal vector of the parallelogram with the tail at the tails of the vectors A and B is the resultant, and denoted with A plus B. By the construction of the parallelogram, we can see that the sum of two vectors is commutative. That is, A plus B is equal to B plus A, meaning the order of the vectors does not matter in this operation. We can also see that the sum of vectors is also associative. If we take the vector A and the vector B, where we translate the tail of B to the head of A, and the vector C, by translating its tail to the head of the previous vector, Then we can construct the vector a plus b. And the vector b plus c. Now the resultant a plus b plus c can be constructed in two different ways. Either we take the sum of the vector a plus b and the vector c, or we take the sum of the vector a and the vector b plus c. Then we can write that the vector a plus b, plus the vector c is equal to the vector a plus the vector b plus c, which shows the sum of vectors is associative. If to denote the angle between the vectors a and b with alpha in the parallelogram, we can write that the angle at the head of the vector a is equal to pi minus alpha. Then we can determine the length of the resultant a plus b by using the cosine theorem, which gives a squared plus b squared, minus 2ab times cosine pi minus alpha. By virtue of the trigonometric identity for the addition of angles in the argument of the cosine function, the last term in the expression reduces to 2ab times cosine alpha. If we know the lengths of the vectors a and b, and the angle between a and the resultant a plus b, then we can compute the length of their resultant. Now, if beta is the angle between the vector a and the resultant a plus b, then we can use the sine theorem to determine the direction of the resultant, since the sine of the angle beta is equal to the ratio of the length of the vector b to the length of the resultant a plus b, multiplied by the sine of the angle alpha. Let us continue with some further basic vector operations. Based on the sum of two vectors, we can introduce the negative of a vector, which is also a vector with the same length, pointing into the opposite direction. Here we can see the opposite of the vector a, which is denoted with minus a. In the vector equation we can see that the sum of these two vectors is equal to the zero vector, where the zero vector has zero length and an arbitrary direction. The vector equation also shows that the lengths of the vector a and minus a are equal. They are also parallel but they have opposite orientations. Then we can define the subtraction of two vectors, as the sum of the first vector and the negative of the second one. If we have the vectors a and b, then we take the opposite of b, which is minus b, and translate it to the head of the vector a. Now we can take the sum of the vectors a and minus b, where we denote the resultant with a minus b. We see that in the vector equation the vector a minus b is defined by the sum of a and minus b. The next operation is the multiplication of a vector with a scalar. For a vector a, we can give any real number, denoted with c, for which we define the multiplication of the vector a with the scalar c, or c times a, as a vector pointing to the direction of a but with the length equal to the magnitude of c times the length of a. By using this operation, we can also define the unit vector which is unit length. For a vector a, the unit vector Ea is defined as the multiplication of a with the inverse of its length. Then the length of unit vector Ea is equal to 1, and it points into the direction of the vector a, as we see in the figure. When we use vectors in mechanics, we also need to know how to decompose vectors in terms of other vectors. We already mentioned that a vector can be constructed by using a set of other vectors, that is, it can be the resultant of the sum of other vectors. For example, let's take the vector a, which can be constructed from the vector b, translated its tail to the one of the vector a, and the vector c, which points from the head of the vector b to the head of the vector a. Then the vector sum of b and c gives the vector a, and we can say the vector a is decomposed to the vectors b and c. But we can have many other ways to make such decomposition. For example, we can take the vector d, the vector e, and the vector f. Their vector sum also gives the vector a. What we use generally for the decomposition is a set of coordinate basis vectors. If we consider the rectilinear or Cartesian coordinate system, with the axes x, y and z, we can define the basis vectors ex, ey and ez of the coordinate system. These vectors are unit vectors, that is, they have unit length. They are also mutually perpendicular to each other, as we can see in the figure. Now, if we consider the vector a with the tail at the origin and the head at the point P, we can determine the angle alpha between the vector a and the basis vector ex. Similarly, we can specify the angle beta between the vector a and the basis vector ey, and the angle gamma between the vector a and the basis vector ez. We can also project the distance of point P, or the length of the vector a, onto the coordinate planes and axes. These projected distances can be calculated from the length of the vector a and the angles defined here. And they are called as the components of the vector in the Cartesian coordinate system. The projection of the length of a onto the x-axis is denoted with ax, and it is equal to a times cosine alpha. It is called the components of the vector a in the direction of the x-axis. The components of the vector A in the direction of the y-axis is denoted with AY and it is equal to A times cosine beta. The third component AZ is in the direction of the z-axis and it is equal to A times cosine gamma. The cosines of the angles alpha, beta, and gamma are called directional cosines, since they determine the direction of the point P with respect to the axes of the coordinate system. Then the decomposition of the vector A with respect to the coordinate basis vectors EX, EY and EZ is the linear combination AX times EX, plus AY times EY, plus AZ times EZ. Since the coordinate basis vectors are fixed, the vector A is completely determined by the coordinates AX, AY and AZ. This linear combination is called as the basis expansion of the vector A, or we say that the vector is expanded in the basis EX, EY and EZ. The length of the vector A can also be determined in the terms of its coordinate base expansion. If we denote the projection of its length onto the xy-plane with h, then we can use the Pythagorean theorem and write that the square of the length of the vector A is equal to h squared plus the square of AAZ. If we apply the Pythagorean theorem again, we can write h squared as the sum of ax squared and ay squared. Then a squared is the sum of the squares of ax, ay and az. That is, the length of the vector A is the square root of the squared sum of its components in the Cartesian coordinate system. As a result of the basis expansion, any vector equation is equivalent to three scalar equations. That is, if the vector A is equal to the vector B, it means we have three component equations, namely, ax is equal to bx, ay is equal to by, and az is equal to bz. Then we can work with the scalar equations by determining the components, as the expansion of the vector equations in the given coordinate basis. The last two vector operations which we use in kinematics are the scalar product and the cross product of vectors. Let us start with the scalar product. For the vectors A and B, we can translate the vector B to the tail of the vector A and determine the angle phi between them. We denote the scalar or dot product of the vectors A and B with A dot B, and define it as the multiplication of the magnitudes of I and B with cosine phi. If we denote the projection of the vector A onto the vector B with AB, then AB is equal to A times cosine phi. Now, we can also write the dot product of the vectors A and B as AB times the length of B. As a consequence of the definition of the dot product of the vector A with itself is equal to the square of the length of the vector A. Then we can say that the length of a vector is the square root of its dot product with itself. If we exchange the vectors A and B, then the dot product of the vector B and the vector A will be equal to B times A times cosine 2 pi minus phi, as we measure the angle from the vector B now. But this result is equal to AB times cosine phi, that is, the dot product is commutative, which means that A times B is equal to B times A. We also see from the definition, if the length of the vector A or B is 0 or A is perpendicular to B, then the dot product of A and B vanishes. Since the basis vectors of the Cartesian coordinate system are mutually perpendicular to each other, their scalar products with each other vanish. The dot products of the basis vectors with themselves give unity, since each of them is a unit vector. These properties of the coordinate basis are very useful, if we expand the vectors A and B with respect to the basis vectors in the scalar product. We can also show that the scalar product is distributive, and we can take the dot product for each term in the parentheses. The terms with the dot products of different basis vector vanish, while in the terms with the dot products of the same basis vector, the dot product gives 1. As a result, the scalar product of the vectors A and B will be equal to AX times BX, plus AY times BY, plus AZ times BZ. The last vector operation we consider here is the vector or cross product. We can use the vectors A and B again with the angle phi between them. The vector product of the vectors A and B is defined as a vector, denoted with A cross B, which is perpendicular to both A and B. The vectors A, B and the vector A cross B forms a triplet with the right-hand rule. The length of the vector product of A and B is defined as the length of A times the length of B times sine phi. It follows from the definition applying the right-hand rule that the cross product is anti-commutative, that is, A cross B is equal to minus B cross A. It also follows from the definition, if the length of A or the length of B vanishes or the vectors A and B are parallel, then their cross product vanishes. The cross product of any two different coordinate basis vectors always gives the third one, with the permutations EX, EY and EZ in the cross product. The cross products of the coordinate basis vectors with themselves vanish, since the vectors are parallel with themselves. We can use these relations in the basis expansions of the cross product, which gives the product with the x components equal to ay times bz minus az times by, with the y component equal to az times bx minus ax times bz, and with the z component equal to ax times by minus ay times bx. After introducing the concepts of scalars and vectors, let us discuss the description of the motion of the bodies in terms of these quantities. We will start with the position of the bodies in space and the distance covered by them during the motion. The position of a point-like body or a point mass in the space is always determined with respect to some reference point, which is attached to the frame of reference. Here the cube represents the frame of reference and one of this corner is chosen as the reference point O. The position of the point mass M is then given relative to this point. Then the position vector R describes the position the point mass with respect to the reference point O. The tail of the position vector R is at the reference point O, and it points to the location of the point mass M. Since the body is moving, its position is also changing in time. Then the momentarily position of the body is given by the vector function rt for each instant of time. The parameter of the vector function r is the time t. As time passes by, the vector function always gives another position vector pointing to the moving body for a given time t. Here the position vectors at the time t0, t1 and t2 describe the momentary position of the point mass m on its path or trajectory as it moved along a curve. All the three position vectors determine the location of the point mass with respect to the reference point O. We have not attached any coordinate system to the frame of reference yet. We only used a reference point tied to the frame, and that was enough to introduce the vector function rt to determine the position of the point mass. The length of the position vector r is the distance of the point mass m from the reference point O. The SI unit of the length, or the distance in space, is the meter, and this unit is denoted by the letter m. The meter is defined as the length of the path traveled by the light in vacuum during a time interval of about 1/300 million of a second. We can see the platinum iridium bar with the length representing the standard meter in the photo. The capital letter L denotes the length as a physical quantity, and the L in angle brackets means the unit of length. As we already stated, the SI unit of length is the meter, but its decimal multiples and submultiples, like millimeter, centimeter and kilometer, are also in usage. The other important physical unit in kinematics is the unit of time, which we have already seen in the definition of meter. The SI unit of time is the second, abbreviated with the letter S. The capital letter T denotes time as a physical quantity, and T in the angle brackets denotes the physical unit of time. The decimal submultiples of second are also in usage, whereas the multiples of it, like the minute, hour and year, are not its decimal multiples but based on the clock and the calendar. The modern definition of the second is given as a fraction of the duration of a transition process between different states of the cesium-133 atom. The next kinematic quantity we will define is the velocity of moving bodies. We determine the motion of a body as the change of its position in space. If we have a ball on the floor moving from one place to another, we can measure the distance s between the initial and the final positions of the ball. Another relevant quantity in the description of motion is the time interval t in which the body changed its position. Then the speed of the motion, or how fast the body moves, is characterized with the ratio of the distance between the two positions to the time interval of the change in position. Based on this concept, we can define the velocity of a body by two measured data. The first one is the speed, that is the ratio of the distance measuring the change in its position to the time of the travel. We denote the speed with the letter v, which is equal to the distance s divided by the time t. Then the unit of the speed is the unit of length divided by the unit of time, which has the SI unit meter per second. Other units can also be used, for example kilometer per hour, which is also a popular choice in measuring speed. The second measured data used for the concept of velocity is the direction of the motion, which can be described by a vector with the tail at the initial position of the body pointing in the direction of the motion. If the speed, that is the length of the velocity vector, is constant, then we talk about uniform motion. If the direction of the velocity is constant, then we talk about motion along a straight line. Since the motion of a body is the change in its position in time, a body moving along a path can be described with the position vector in different instances of time. Here we have a space curve along which a point mass moves. At the time t, the point mass is at the point P. If we chose a reference point O attached to a frame of reference, then the position vector r with the time parameter t will describe the position of the point mass at the point P. At the time t plus delta t prime, the moving point mass will reach the point P double prime on the curve, which is described with the position vector r evaluated at the time parameter t plus delta t prime. We can also draw the difference of the position vectors rt plus delta t prime and rt, which is denoted by the green arrow with the label delta r prime pointing from the point P to P double prime. This vector can be called the distance vector, which points from the original position to the new position. The length of the distance vector will give the distance between these positions. Now we can also show the ratio of the difference delta r prime in space to the difference delta t prime in time. This is denoted by the blue arrow with the tail at the point P, and it has the same direction as the difference delta r prime, since the division with the value delta t prime is just a multiplication of the vector delta r prime with the scalar 1 over delta t prime. We can also write the different quantities related to the motion in a table. For given instances of time, the position of the point mass will be written in the table together with the distance vectors and the rate of change in space, that is the ratio of the difference in the position vectors to the difference in time. For the time t plus delta t prime, we have the position vector rt plus delta t prime. And the distance vector delta r prime is just the difference of the positions rt plus delta t prime and rt. And their ratio is delta r prime divided by delta t prime. Let us choose another point P prime on the curve between P and P double prime. Now the position vector pointing to the point P prime is given by rt plus delta t, where the difference delta t is less than delta t prime. The new difference vector pointing from the point P to P prime is labeled with delta r. The ratio delta r divided by delta t is also depicted in the figure. Now we can fill the next row in the table with the new data. At the time t plus delta t, we have the position vector rt plus delta t. The distance vector delta r of the positions rt plus delta t and rt. And the ratio delta r divided by delta t. As we saw, the length of the difference delta r gives the distance of the points P and P prime. Whereas the distance covered by the moving point mass between the points P and P prime is the arc length of the curve between these points. Now we can choose a new point on the curve between P and P prime, which means a difference in time smaller than delta t, and construct the difference and the ratio vectors corresponding this new point. Then we can continue this process with a series of points gradually approaching the point P. We can see in the figure that the difference and the ratio vectors are approaching the tangent of the curve at the point P, as we chose points closer and closer to P. The length of the difference vector is also getting closer and closer to the arc length of the curve between the point P and the series of points approaching P. In this limiting process we get infinitesimally close to the point P, where we also have the infinitesimal difference dt in time. The position vector will be rt plus dt, and the infinitesimal distance vector dr will be the difference between rt plus dt and rt. Then their ratio will be dr divided by dt, which is formally the derivative of the position vector at the point P. As a result, the ratios of the distance vectors approach the tangent to the curve, which is the derivative of the position vector r, as delta t tends to 0. In the figure, the tangent to the curve at the point P is the derivative dr over dt of the curve at that point. We have already seen that the difference of the distance vector approaches the arc length of the curve measured between the 2 points at the tail and the head of the distance vector. Then the length of the derivative of the position vector with respect to the time t at a given point on the curve is equal to the derivative of the arc length measured along the curve with respect to the curve parameter t at that point. Now we can conclude that the velocity vector of a moving body is the derivative of its position vector with respect to the time. That is, the vector v is equal to dr over dt. As we saw in the case of the speed, its unit is the unit of length divided by the unit of time. By definition, the velocity is a vector function similar to the position vector, since we derived it by differentiating the position vector with respect to the curve parameter. That is, the length of the velocity vector vt gives the speed of the body at the instance t of time at the point P. Which means the magnitude of the velocity vector is the time derivative of the arc length measured along the path of the moving body. The direction of the velocity vector vt gives the instantaneous direction of the motion, which is the tangent to the path of the motion at the point P. The next kinematic quantity which we introduce here is the acceleration of a moving body. If we consider a general case of motion, the velocity of a moving body can change with respect to both its magnitude and its direction in time. Then we can follow the same procedure which we used to define velocity. The only difference is that we are approximating the change of the vector representing the velocity instead of the position vector along the path covered by the moving body. Here we can see the spatial curve representing the path of the moving body. After having chosen the reference point O, we can use the position vector rt to describe the momentarily point P of the moving body along the curve at the instance t of time. Then the velocity of the moving body at the point P is the tangent vt to the curve. At the time t plus delta t, the moving body reaches the point P' on the curve, which has the position vector rt plus delta t. The velocity of the body at the point P' is then the tangent vt plus delta t. We can see in the figure that the direction of the velocity is different at the point P' from the one at the point P. This means that the velocity vectors are different in the 2 points even if their lengths are the same, that is, even if the body is moving with a constant speed along the curve. Now we can take the original velocity vector vt in the point P and translate the tail of the new velocity vector vt plus delta t to its tail. Then we construct their difference delta v, given by the subtraction of the vector vt from the vector vt plus delta t. We can calculate the ratio of the difference delta v to the elapsed time delta t, which is also a vector pointing to the direction of delta v. As the elapsed time approaches 0, the limit of this ratio gives the derivative of the velocity vector v with respect to the time parameter t. Then we can define the acceleration vector of a moving body as the derivative of its velocity vector with respect to time, that is, as the second-order derivative of its position vector with respect to time. We denote the acceleration vector with the boldface letter A. Its physical unit is the ratio of the unit of length to the square of the unit of time, following from its definition. Then its SI unit is meter per second squared. We talk about accelerating motion if the acceleration vector of a moving body does not vanish, which means the velocity vector of the moving body is not constant in time. As we have already seen, if a body moves along a curve it has an accelerating motion since the direction of the velocity vector is changing in time, even if the body is moving with constant speed. This means that only the uniform linear motion has no acceleration, since both its speed and direction are constant. By introducing the basic kinematic quantities, we are able to describe the motion of bodies. If we apply these quantities we can formulate the equations of motion for the moving bodies, which give a unique mathematical representation of the motion. In kinematics the equation of motion of a point-like particle is the vector function of the position, that is its position vector r, which is a function of time. Here we can see a curve along which a point-like body or particle moves. At the time t0 we can find the body in the point P and at the time t1 it will be in the point P'. Our t0 and our t1 are the two position vectors pointing from the reference point O to the positions P and P' of the particle. If the position vector r of the body is given as a function of time, then the velocity and the acceleration of the body can be determined by applying the definitions of these kinematic quantities. In order to obtain the velocity, we only need to determine the derivative of the position vector r with respect to time. In the next step we can calculate the acceleration by differentiating the velocity vector with respect to time. If the explicit forms of the position vector, the velocity, and the acceleration are given as the functions of time, then we have a complete description of the motion of the given body. In kinematics we call these equations the equations of motion. Since the equations of motion are differential equations, we can also talk about the integration of the equations of motion. If the acceleration is given as a function of time, then the change in velocity can be determined between some instances of time, let's say between t1 and t2. This change, that is vt2 minus vt1 is given by the integral of the acceleration over the time interval between t1 and t2. If the velocity is given as a function of time, then the change in the position vector can also be determined between t1 and t2. This change, that is our t2 minus our t1 is given by the integral of the velocity over the time interval between t1 and t2. Since the distance covered by the moving body is the arc length measured along its path, the distance s is just the integral of its speed or length of the velocity over the interval between t1 and t2. In the definition of the kinematic quantities we used only a reference point attached to any frame of reference. However, in order to describe the motion with mathematical formulae, we need to attach a coordinate system to a reference point. Then the position of a point mass can be described in this coordinate system. This cube represents the frame of reference we have chosen, and we will describe the motion of a point mass with respect to this frame. We pick one of the corner of the cube as the reference point O, and we attach a coordinate system to this point. We can choose any orientation of the axes of the coordinate system. For example, we can align them to the edges of the cube or to the shape of the trajectory of the moving point mass. In the practice we can use many different coordinate systems, but we already have seen the most popular ones. The first one was the Cartesian coordinate system with the Cartesian coordinates x, y, and z. In this coordinate system, the curve along which the point mass moves can be described with the Cartesian coordinates as functions of time. The position vector r of the body at any point P on the curve is represented with the coordinate functions xt, yt, and zt. By the definition of the coordinate functions, their ranges run from -infinity to +infinity, covering the entire space. The next coordinate system we mentioned was the cylindrical coordinate system with the coordinates ρ, phi, and z. These coordinates are interpreted as functions of time when we describe any point P on the curve along which the point mass moves. Then the position vector r of the moving body is represented by the coordinate functions ρt, phi t, and zt. Here the range of z still covers the entire real line between minus and plus infinity, but ρ is restricted to the non-negative numbers, and the azimuthal angle phi runs between 0 and 2 pi. The last coordinate system we considered was the spherical polar coordinate system with the coordinates r, theta, and phi. These coordinates describe any point P on the curve along which the point mass moves as functions of time. Here the position vector r of the moving body is represented by the coordinate functions rt, theta t, and phi t. Now the radial coordinate r is defined over the non-negative real numbers. The polar angle theta covers the range between 0 and half of pi, and the azimuthal angle phi runs between 0 and 2 pi. The cylindrical and spherical polar coordinate systems are special cases of the curvilinear coordinate system. For many types of motion it is more convenient to use curvilinear coordinates when we describe the position of a point in space, since these coordinates are more suitable for the geometrical arrangement of the given case, that is, they can be adapted to the symmetries of the problem. Let us denote the curvilinear coordinates of an arbitrary point P in the space with the triplet u1, u2 and u3. The most convenient method to define these coordinates when they are given as functions of the Cartesian coordinates. For the point P described with the rectilinear coordinates, we can specify the coordinate transformations for the curvilinear coordinates u1, u2, and u3 as functions of x, y and z. We also have the inverse coordinate transformations for the Cartesian coordinates as functions of the curvilinear ones. That is, we have two equivalent descriptions of the position of P in the coordinate space. We can draw the coordinate lines through the point P, for which one of the curvilinear coordinates is running over its domain, while the other two coordinates have fixed values, given in the point P. As opposed to the Cartesian coordinates, these coordinate lines are not necessarily straight lines and not even mutually orthogonal to each other in the point P. The Cartesian coordinates are regular in the sense that the coordinate lines are the x, y and z axes, which are perpendicular to each other. We can also consider the point sets, where one of the coordinates is fixed while the other two coordinates are arbitrary. These two-dimensional point sets are called coordinate surfaces. In the case of the Cartesian coordinates, for x is equal to a constant we have a family of planes parallel with the yz plane. Here we see the plane for x equal to 0 in one of the octants of the coordinate system. For the points defined by y equal to a constant, we have planes parallel with the xz plane. Here we also see the plane for y equal to 0 in one of the octants of the coordinate system. The points for z equal to a constant represents the planes parallel with the xy plane. Here we see the plane for z equal to 0 in one of the octants of the coordinate system. The coordinate surfaces of the curvilinear coordinates are generally not planes. For the points defined by u1 equal to a constant, we have surfaces on which the coordinate lines u2 and u3 run. For the points defined by u2 equal to a constant, the coordinate surface contains the coordinate lines u1 and u3. The coordinate surface for points defined by u3 equal to constant has the coordinate lines u1 and u2. It follows from these definitions that the coordinate lines are the intersections of the coordinate surfaces. In the case of the Cartesian coordinates they coincide with the x, y and z axes. In the case of the curvilinear coordinates, we can only say that the coordinate lines are the intersections of the coordinate surfaces. The Cartesian basis vectors ex, ey, and ez point from the origin into the direction of the axes. They are mutually orthogonal and can be considered as the normal vectors of the yz, xz and the xy planes respectively. The curvilinear coordinate basis vectors e1, e2 and e3 are not necessarily orthogonal to each other, but they are the normal vectors of the coordinate surfaces in the point P. If we want to describe the motion in a curvilinear coordinate system, we need to determine the explicit forms of the basis vectors of the coordinate system. We can use the coordinate transformations between the Cartesian and the curvilinear coordinates to obtain these expressions. The basis vectors of the Cartesian coordinate system are already given. Their directions are determined by the axes of the coordinate system and they have unit length. Now we consider a curvilinear coordinate system with the coordinates u1, u2, and u3, and determine the explicit forms of its basis vectors e1, e2, and e3. In this calculation, we will use the functions of inverse coordinate transformations, which map the curvilinear coordinates to the Cartesian ones. The natural basis vectors of the curvilinear coordinates can be written as the linear combinations of the Cartesian basis vectors, where the coefficients are the partial derivatives of the Cartesian coordinates with respect to the curvilinear ones. That is, the natural basis vector gi for the coordinate ui with the index I running from 1 to 3 is given by the partial derivative of x with respect to ui times ex, plus the partial derivative of y with respect to ui times ey, plus the partial derivative of z with respect to ui times ez. We can conclude that the components of the natural basis vectors in the Cartesian coordinate system are the partial derivatives of the Cartesian coordinates with respect to the corresponding curvilinear coordinates. It can be shown that the vectors are linearly independent from each other, therefore they form a basis. The length of each basis vector is given by the square root of the squared sum of its components, which is not necessarily unity. Now, the coordinate basis vectors of the curvilinear coordinates are defined by the normalized natural basis vectors. That is, ei is equal to gi divided by the length of gi, where the index I is running from 1 to 3. Here we can see the explicit forms of the coordinate basis vectors, which are complicated expressions. However, we can use the Jacobian j of the coordinate transformations between the Cartesian coordinates and the curvilinear ones to compute the basis vectors. In fact, the columns of the Jacobian will help us to determine them. Since each column of the matrix J contains the nominator of the fraction defining the corresponding basis vector, it is enough to read out their components from the column vectors of the matrix, denoted with J1, J2 and J3. The only missing factor is the normalization, which can be computed from the squared sum of the column vectors. Then each column vector is equal to the corresponding basis vector times the length of that column vector. We apply this simple method to determine the basis vectors of the cylindrical and spherical polar coordinates. Let us start with the computation of the basis vectors for the cylindrical coordinates. Here the curvilinear coordinates u1, u2, and u3 are the quantities ρ, phi and z, which are defined in this figure. We also have the explicit forms of the Cartesian coordinates as the functions of the cylindrical ones. By using these functions, we would like to determine the basis vector e ρ, which is the unit tangent of the ρ line translated to the point P. The basis vector e phi, which is the unit tangent of the phi line translated to the point P. And the basis vector ez, which is the unit tangent of the z line translated to the point P. We know that the position vector pointing at P has the basis expansion ρ times e ρ, plus c times ez. By taking the derivatives of the coordinate transformation with respect to ρ, phi, and z, we can compute the Jacobian of the transformation. Now we can determine the basis vectors from the column vectors of the Jacobian. E ρ is given by its first column vector. Since the length of this vector is the square of sine phi plus the square of the cosine phi, which is 1, the components of E ρ are the same as the column vector. Its x component is cosine phi and its y component is sine phi. Similarly, the second column vector gives the basis vector e phi. Since the length of the second column vector is ρ, we need to divide this vector with this length to obtain the basis vector. Then the x component of the basis vector e phi is minus sine phi, and its y component is cosine phi. The third column with its unit length shows that the third basis vector is simply ez. We can follow the same procedure for the spherical polar coordinates. Here the curvilinear coordinates u1, u2, and u3 are r, theta, and phi, with the definitions in this figure. The coordinate transformations are somewhat more complicated than in the case of the cylindrical coordinates. The basis vector er is the unit tangent of the r line at the point P. The basis vector e theta is the unit tangent of the theta line at the point P. And the basis vector e phi is the unit vector of the phi line at the point P. The form of the position vector is simply r times er. The derivatives of the Cartesian coordinates with respect to the spherical polar ones give the Jacobian of the coordinate transformation. Then we can determine the basis vectors from the columns of the matrix again. The first column of the matrix gives the basis vector er. Since the length of the first column is equal to 1, the components of the column vector are equal to those of the basis vector er. The x component of the basis vector is sin theta times cosine phi. Its y component is sin theta times sin phi. And its c component is cosine theta. The second column vector of the Jacobian determines the basis vector e theta, where the length of the column vector is r. If they divide its components by r, we obtain the components of the basis vector e theta. Then its x component is cosine theta times cosine phi. Its y component is cosine theta times sin phi. And its c component is minus sin theta. The last column vector of the Jacobian determines the basis vector e phi. The length of this column vector is equal to r times sin theta, and the column vector divided by this length will be the basis vector. Then its x component is equal to minus sin phi, and its y component is cosine phi. Now we obtain the full set of the coordinate basis vectors, both the cylindrical and spherical coordinate systems. If we want to describe the velocity and the acceleration of a moving body in the terms of cylindrical coordinates, we need to express the parametric derivatives of the basis vectors as their linear combinations. In the cylindrical coordinate system, the coordinates ρ, phi and z become the functions of the time parameter t. Therefore, we have to differentiate these functions in the basis vectors e ρ and e phi with respect to t to obtain the derivatives of these basis functions. Since the basis vector ez does not depend on the parameter t, its derivative with respect to it will vanish, which means it is a constant vector. Let us start with the computation of the first-order derivatives of the basis vectors. If we differentiate the basis vector e ρ with respect to t, then the x component of the derivative vector will be minus phi dot times sin phi, and its y component will be phi dot times cosine phi. Now we can factor out the derivative of phi, and the rest of the terms gives nothing but the basis vector e phi. Then the parametric derivative of the basis vector e ρ is equal to the basis vector e phi multiplied by the parametric derivative of the azimuthal angle phi. Similarly, the x component of the derivative of the basis vector e phi is minus phi dot times cosine phi, and its y component is minus phi dot times sin phi. After factoring out the derivative of the azimuthal angle, the rest of the terms gives minus 1 times the basis vector e ρ. Then the parametric derivative of the basis vector e phi is equal to the basis vector e ρ multiplied by minus the parametric derivative of the azimuthal angle phi. This is an important result, which shows that the parametric derivatives of the basis vectors can be expressed in the terms of the basis vectors themselves. The second-order derivative of the basis vectors can be calculated by differentiating their first-order derivatives. Then the second-order derivative of the basis vector e ρ is equal to phi double dot times e phi, plus phi dot times e phi dot. Since e phi dot is equal to minus phi dot times the basis vector e ρ, the second term in the right-hand side can be written as minus phi dot squared times the basis vector e ρ. The second-order derivative of the basis vector e phi is equal to minus phi double dot times e ρ, minus phi dot times e ρ dot. Here we can also replace the derivative of the basis vector e ρ in the second term with phi dot times e phi. Then the second term can be written as minus phi dot squared times the basis vector e phi. As a result, we could also express the second-order parametric derivatives of the basis vectors as the linear combinations of the basis vectors themselves. In fact, the second-order derivatives are not necessarily needed to describe the acceleration in cylindrical coordinates, but we present their derivations here for the sake of completeness. Before differentiating the velocity vector written in cylindrical coordinates, we can replace the first-order derivatives of the basis vectors with the expressions in the first purple box. Then the differentiation of the velocity leads to equations containing the first-order derivatives of the basis vectors, which can be replaced with the same expressions again. We can provide some geometric interpretations for the derivatives of the basis vectors of the cylindrical coordinate system, which can be demonstrated in the figure. Here we can see the point P described with the coordinates ρ, phi and z. At the point P, we can draw the basis vectors e ρ, e phi and ez. If we translate the point P into the point P' along the curve phi equal to constant, the point P' can be described with the coordinates ρ', phi and z'. Since the azimuthal angle phi is constant, its derivative vanishes. Therefore, the derivatives of the basis vector e rho and e phi also vanish. That is, the basis vectors do not change along the phi line. As a result, the basis vectors in the point P' are the same as the original ones in the point P. If we translate the point P to the point P double prime along with the circle of constant rho in the z-plane, the coordinates of the point P double prime will be rho, phi double prime, and z. Since we change the azimuthal angle, its derivative does not vanish. Neither do the derivatives of the basis vectors. As a result, the basis vectors are changing as we move the point P along the constant rho circle. For the basis vectors erected in the point P double prime, both the vectors e rho and e phi point into different directions compared to those in the point P. We also saw that the derivatives of the basis vectors are proportional to the derivative of the azimuthal angle, and the derivative vectors point into the directions of the basis vectors. This statement can be demonstrated in this figure with the z-plane lying in the plane of the figure. Here we see the constant rho circle is passing through the point P given by the position vector r. The basis vector e rho at the point P has the same direction as the position vector. If we rotate the position vector with the angle delta phi, we move the point P into the point P'. Then the basis vector at P' points into a new direction. We can translate this basis vector to the point P, and construct the difference between the translated basis vector and the original one, labeled with e rho dot. We can see that the difference vector is indeed the derivative of the basis vector if we translate it along the arc between the points P and P'. If the point P' approaches the point P, then the angle delta phi becomes infinitesimally small. As a result, the difference vector becomes perpendicular to the position vector, that is, it becomes a tangent to the circle. And its length will be equal to the change delta phi in the azimuthal angle. Then the derivative of the basis vector e rho is a tangent to the constant rho circle, that is, it has the same direction as e phi do, and it is proportional to the derivative of the azimuthal angle. We can use the same procedure in the case of the derivative of the basis vector e phi. Here the basis vector e phi is depicted at the point P, which is the tangent to the circle at P. If we rotate the position vector with the angle delta phi again and move the point P into the point P', then we can draw the basis vector e phi at P', which will be the tangent to the circle at that point. Let us transport this vector to the point P. We can see that the angle between the transported basis vector and the original one is equal to delta phi. We take the difference of the transported basis vector and the original one, which is labeled by e phi dot. This difference vector can be transported to the circle between the points P and P', and we can take the limit as angle delta phi approaches 0. In this limit, the difference vector will point in the same direction as the position vector do. Therefore, it will be parallel with the basis vector e rho, but it points to the opposite direction. Since the angle between the transported basis vector and the original one is equal to delta phi and this angle is infinitesimal, the length of the difference vector is the change in the angle again. Then we see that the derivative of the basis vector e phi is perpendicular to the tangent to circle in the point P, that is, it has the opposite direction to e rho, and it is proportional to the derivative of the azimuthal angle. We can differentiate the basis vectors of the spherical polar coordinate system in the same way. The coordinates r, theta, and phi are the functions of the parameter t now. If we consider the expressions of the basis vectors, we can see that these vectors depend only on the angles theta and phi. Therefore, the derivatives of the basis vectors will contain the derivatives of the angles. Let us compute the first-order derivatives of the basis vectors. In order to obtain the derivative of the basis vector er, first we apply the Leibniz rule and the chain rule for its x-component, which is the product of sine theta and cosine phi. As a result, the x-component of the derivative of the basis vector is equal to theta dot times cosine phi, minus sine theta times phi dot times sine phi. We can apply the same rules to the differentiation of the y-component of the basis vector er. Since the y-component is given by sine theta times sine phi, its derivative is equal to theta dot times cosine theta times sine phi, plus sine theta times phi dot times cosine phi. Similarly, since the z-component of the basis vector er is cosine theta, its derivative is equal to minus theta dot times sine theta. Now we can factor out the expression phi dot times sine theta from the second and the fourth terms in the right-hand side. This gives phi dot times sine theta, times the sum of minus sine phi times ex and cosine phi times ey. We can also factor out the derivative of theta from the rest of the right-hand side, which gives theta dot times cosine phi times ex plus cosine theta times sine phi times ey minus sine theta times ez. Now we recognize that the expressions in the parenthesis in the first term give the basis vector e phi, whereas the expressions in the parenthesis in the second term give the basis vector e theta. Then the derivative of the basis vector er can be written as phi dot times sine theta times e phi, plus theta dot times e theta. We can follow the same procedure when we compute the derivative of the basis vector e theta. The x component of e theta is cosine theta times cosine phi, and its derivative can be written as minus theta dot times sine theta times cosine phi, minus cosine theta times phi dot times sine phi. The y component of the basis vector e theta is cosine theta times sine phi, and we can write its derivative as minus theta dot times sine theta times sine phi, plus cosine theta times phi dot times cosine phi. The z component of e theta is simply minus sine theta with the derivative of theta dot times cosine theta. If we factor out minus theta dot from the first, the third, and the last terms, we obtain minus theta dot times sine theta times cosine phi times ex plus sine theta times sine phi times ey plus cosine theta times ez. We can also factor out the term phi dot times cosine theta from the second and the fourth terms, which gives plus phi dot cosine theta times the sum of minus sine phi times ex and cosine phi ey. Now we see that the terms in the parenthesis of the first term give the basis vector er, whereas the terms in parenthesis of the second term are equal to the basis vector e phi. Then the derivative of the basis vector e theta is equal to theta dot times the basis vector er, plus phi dot times cosine theta times the basis vector e phi. If we want to compute the derivative of the basis vector e phi, we take another route. The x component of e phi is simply minus sine phi with the derivative minus phi dot times cosine phi. Its y component is cosine phi with the derivative minus phi dot times sine phi. Now we can multiply both the x and the y components of the derivative by the sum of squares of sine theta and cosine theta, which is identically 1. Then we can factor out the expression minus phi dot times sine theta, which gives minus phi dot times sine theta times the sum of sine theta times cosine phi times ex and sine theta times sine phi times ey. If we factor out the expression minus phi dot times cosine theta, we obtain minus phi dot times cosine theta times the sum of cosine theta times cosine phi times ex and cosine theta times sine phi times ey. Finally, we can also subtract the expression phi dot times sine theta times cosine theta from the derivative and the same time add to it. Then the first and the third terms in the right-hand side give minus phi dot times sine theta times er, and the second and the last terms give minus phi dot times cosine theta times e theta. Now we see that we could express the derivatives of the basis vectors in the terms of the basis vectors themselves. The derivative of the basis vector er is the linear combination of the basis vectors e theta and e phi, where the coefficients of the vectors are functions of the angular coordinates and their derivatives. The derivative of the basis vector e theta can be written as the linear combination of the basis vectors er and e phi with the coefficients depending the angles and their derivatives. The derivative of the basis vector e phi is also a linear combination of the other two basis vectors, er and e theta, where the coefficients still depends on the angles and their derivatives. By applying these expressions computed for both the cylindrical and spherical polar coordinates, we can give the first and the second order derivatives of the position vector in these coordinate systems. As we have already seen, the equations of motion of a point-like body in kinematics are the position vector of the body, and its in first and second order derivatives, expressed as vector-valued functions of time. Now let us find out how the equations of motion can be written as component equations in the three coordinate systems presented here. The position vector and its derivatives have the simplest expressions in Cartesian coordinates, since the basis vectors of the Cartesian coordinate system do not depend on time. The position vector r has the x, y and z coordinates in the direction of the x, y and z axes. The coordinate components of its time derivative are simple the derivatives of the x, y and z coordinates. Similarly, the coordinate components of its second order derivative are simple the second order derivatives of the x, y and z coordinates. In the cylindrical coordinate system, these expressions will be more complicated since two of the basis vectors are also changing in time. The position vector r has two coordinate components, ρ in the direction of the ρ coordinate line, and z in the direction of the z-axis. Since the basis vector e ρ depends on the time parameter t, the derivative of the position vector is equal to ρ dot times e ρ, plus ρ times e ρ dot, plus c dot times ez. We have already seen that the derivative of the basis vector e ρ is equal to phi dot times e phi. Then we obtain the first order derivative of the position vector. Its row component is the derivative of the row. Its phi component is rho times the derivative of phi. And its c component is the derivative of z. Now we differentiate the first order derivative of the position vector r. The derivative of the first term of r dot, that is of the expression rho dot times e rho, is equal to rho double dot times e rho, plus rho dot times e rho dot. The derivative of the second term of r dot, that is of the expression rho times phi dot times e phi, is equal to rho dot times phi dot times e phi, plus rho times phi double dot times e phi, plus rho times phi dot times e phi dot. The derivative of the third term of r dot, that is z dot times ez, is simply z double dot times ez since ez is constant. We see that the second order derivative of r contains the derivatives of the basis vectors e rho and e phi, which we already computed. Therefore we can substitute them into this expression. Then we obtain the components of the second order derivative of the position vector. Its rho component is rho double dot minus rho times phi dot squared. Its phi component is rho times phi double dot minus 2 times rho dot times phi dot. And its c component is simply z double dot. We can follow the same procedure in the case of the spherical polar coordinate system. In spherical coordinates, the expression of the position vector r is very simple. It is r times er. Then the derivative of the position vector is given by r dot times er, plus r times er dot. Here we already know the derivative of the basis vector er, which we can substitute into the derivative of position vector r. Then the derivative of the position vector r is the following. Its r component is simply r dot. Its theta component is r times theta dot times sine phi. And its phi component is r times phi dot. Now we differentiate the derivative of the position vector r. The derivative of the first term in r dot, that is of the expression r dot times er, is given by r double dot times er plus r dot times er dot. The derivative of the second term in r dot, that is of the expression r times theta dot times sine phi times e theta, consists of four terms. R dot times theta dot times sine phi times e theta. Plus r times theta double dot times sine phi times e theta. Plus r times theta dot times phi dot times cosine phi times e theta. Plus r times theta dot times sine phi times e theta dot. The derivative of the third term in r dot, that is of the expression r dot times phi dot times e phi, is equal to r dot times phi dot times e phi. Plus r times phi double dot times e phi. Plus r times phi dot times e phi dot. Besides the expression of the derivative of the basis vector er, we also computed the derivatives of the basis vectors e theta and e phi, as we can see in the left-hand side of this box. We can eliminate the derivatives of the basis vectors by substituting these expressions into the second-order derivative of the position vector r. Then the r component of the second-order derivative is equal to r double dot, minus r times theta dot squared times the square of sine phi, minus r times phi dot squared. Its theta component is given by r times theta double dot times sine phi, plus r dot times theta dot times sine phi, plus 2 times r times theta dot phi times cosine phi. Its phi component is equal to r times phi double dot, plus 2 times r dot times phi dot, minus r times theta dot squared times sine phi times cosine phi. Now we can use these results to give the components of the different kinematic quantities in these coordinate systems. Then we can list the coordinate expressions of kinematic quantities in all the three coordinate systems. Here we show a table with the columns for the Cartesian, the cylindrical, and the spherical polar coordinates. In the first row we specify the position vector r, as a function of the time t. For the Cartesian coordinates we have the coordinate functions x, y and z. For cylindrical coordinates the coordinate functions are rho, phi and z. For spherical polar coordinates the coordinate functions are r, theta and phi. The next row contains the velocity v, as a function of the time t. The velocity components in Cartesian coordinates are just the derivatives of the coordinate functions x, y and z. We also show the square of the length of the velocity vector, which is its scalar product with itself. Then it is just the sum of the squares of the derivatives of the coordinate functions. In cylindrical coordinates, the rho component of the velocity is the derivative of the coordinate function rho. Its phi component is equal to rho times the derivative of the azimuthal angle phi. And its c component is simply the derivative of the coordinate z. The square of the length of the velocity is the sum of the square of these components. And it contains squares and quadratic terms of the derivatives of the coordinate functions. In the next column, the components of the velocity and spherical polar coordinate system are shown. Its r component is just the derivative of the coordinate function r. Its theta component is r times sine phi times the derivative of the vertical angle theta. And its phi component is r times the derivative of the azimuthal angle phi. Again, the square of the length of the velocity is the sum of the square of these components, with squares and quadratic terms of the derivatives of the coordinates. In the third line of the table, we can see the acceleration a as a function of time. The components of the acceleration in Cartesian coordinate system are the second-order derivatives of the coordinates x, y and z. The square of the length of the acceleration is the sum of the square of these components. In the next column we can see the acceleration written in cylindrical coordinates. Its rho component is the second-order derivative of rho, minus rho times the square of the derivative of the azimuthal angle phi. The phi component of the acceleration is equal to rho times the second-order derivative of phi, plus 2 times the derivative of rho times the derivative of phi. And its c component is just the second-order derivative of the coordinate z. As in the cases of the previous coordinates, the square of the length of the velocity is the sum of the square of these components. The components of the acceleration in spherical polar coordinates are even more complicated, but they have common patterns. Each component of the acceleration contains the second-order derivative of the corresponding coordinate, and the squares or quadratic terms of the first-order derivatives of the other two coordinates. The square of the length of the acceleration is the sum of the square of these components, which is a very lengthy expression, thus we do not show it. Now we see that the kinematic quantities have the simplest forms in the Cartesian coordinate system, and their components have the most complicated expressions in spherical polar coordinates. However, sometimes the motion of a body exhibits some symmetry, that is, the body moves along some regular curve, for example along a circle in circular motion. In such cases, we can utilize the cylindrical or spherical polar coordinate system, since the components of the kinematic quantities reduce in a great extent. Then the description of motion becomes simple in any of these coordinate systems adapted to the symmetry of the motion. When we consider the curves describing the path or the trajectory of a moving body, we use the elapsed time t as a parameter of the curve. We also saw that the position vector r with the running time parameter t describes the space curve along which a point mass moves as time passes. In this figure, a point mass moving along a curve and it reaches the point P at the instant of time t0. The position P on the curve is given by the position vector rt0. The velocity of the point mass is described by the velocity vector vt0, which is the tangent to the curve at the point P. At the instant of time t1, the point mass will reach the point P', described by the position vector rt1. The velocity of the point mass at the point P' is given by the tangent vector vt1 to the curve at that point. Then we can compute the arc length of the curve between the points P and P'. The arc length s is the integral of the length of tangent of the curve over the interval between t0 and t1, where the tangent is the parametric derivative of the position vector r. The arc length covered by the moving body between the points P and P' is indicated with the green curve. If we fix the point P at the initial time t0 and let the parameter t run with the position of the point P', we obtain the arc length s as a function of t. Then the arc length s is the integral of the length of the tangent of the position vector between the initial time t0 and t. If the length of the tangent does not vanishes over a given interval of time t, then the arc length s is an invertible function of t over that interval, and we can express the time parameter as the function of the arc length s. Then the space curves can be parametrized with respect to the arc length, that is, the position vector can be written as a function of the arc length s. As a result, we can establish the relation between the derivative of the curve with respect to the time parameter t and its derivative with respect to the arc length s. R dot is the derivative of the position vector with respect to the time parameter t. For this derivative we can apply the chain rule, by writing it as the derivative of the position vector r with respect to the arc length s, times the derivative of the arc length s with respect to the time t. Let us denote the derivative with respect to the arc length s by the symbol prime. Then, r dot is equal to r prime times s dot. Since the derivative of the arc length s is the length of the tangent, that is the derivative of the position vector r with respect to the parameter t, we have r prime times the length of r dot. As a result, We can express the derivative of the position vector with respect to the arc length, as the ratio of its time derivative to the length of its time derivative. We also see that the derivative of the position vector with respect to the arc length has a unit length, that is, it is the unit tangent to the curve. The second-order time derivative of the position vector is just the derivative of r dot, which is r prime times s dot. If we apply the Leibniz rule for differentiation of the product in the parenthesis, we obtain two terms. The time derivative of r prime times s dot, plus r prime times s double dot. The first terms gives the square of the time derivative of the arc length s, times the second-order derivative of the position vector r with respect to the arc length. The second term is equal to the second-order derivative of the arc length s, times the derivative of the position vector r with respect to the arc length. Now we have expressed the first and second-order time derivatives of the position vector in terms of its derivatives with respect to the arc length. We will use these expressions to construct a set of basis vectors attached to the moving body. This set of basis vectors moving along an arbitrary curve is called as Frenet-Serret frame after the two French mathematicians and physicists who introduced it. If we want to construct such a frame, we need to ask the question, what are the preferred directions in space at a given point P of a curve RT? The answer is based on the shape of the curve. One of the possible preferred directions is for example given by the unit tangent of the curve T at the point P, which is the derivative of the position vector r with respect to the arc length. The second preferred direction related to the curve RT at the point P is given by the normal vector n, which is the normalized derivative of the unit tangent. We will demonstrate that the normal vector n is perpendicular to the tangent T. The last preferred direction is given by the binormal vector b, which is simply defined as the cross product of the tangent T and the normal vector n. By definition, the binormal vector b is perpendicular to both the tangent and the normal vector, as it is shown in the figure. We will also prove that the triplet T, n and b is an orthonormal set of vectors. By definition, the tangent and the normal vector have unit lengths. Since the length of any vector can be written as the scalar product with itself, the derivative of the scalar product of any unit vector, for example the tangent T with itself, vanishes. As a result, the derivative of T times T is equal to 0. If we apply the Leibniz rule for the derivative of the dot product, we obtain 2 times the dot product of T and T prime. Then the scalar product of T and T prime vanishes, which means the tangent T is perpendicular to its derivative. Since the normal vector n is just the normalization of the derivative of the tangent with respect to the arc length, the tangent T is also perpendicular to the normal vector n. We can compute the length of the binormal vector by applying its definition. Since b is the cross product of T and n, which are perpendicular to each other, the square of the length of b is equal to the length of T squared times the length of n squared. Here the vectors T and n have unit length, thus the vector b is also a unit vector. Then the Frenet-Serret frame, T, n and b forms an orthonormal basis traveling along the curve. We can introduce the notation EI for this basis, with the index I running through the triplet T, n and b. Then the orthogonality condition can be formulated as the dot product of EI and EJ is equal to the Kronecker delta with the indices I and j. If we expand the vector r in this orthonormal basis, we can write r as the linear combination of the basis vectors, where the expansion coefficients of the basis vector EI are given by their dot products with r. We can also expand the derivative of the basis vector EI with respect to the arc length in the basis itself. Here the expansion coefficient is equal to the scalar product of EI prime and EJ. If we take the derivative of the orthogonality condition, then the derivative of the Kronecker delta vanishes, and so is the derivative of the dot product of EI and EJ. Applying the Leibniz rule, we obtain that EI prime times EJ plus EI times EJ prime is equal to 0. This shows that EI prime times EJ is equal to minus EI times EJ prime. If the index I is equal to the index j, both sides of this equation must vanish. Then we just have a vanishing dot product of EI prime and EI, that is any basis vector is perpendicular to its derivative, as we expect for unit vectors. If we define the matrix Aij with the entries A prime times Ej, we see that this matrix is antisymmetric and trace-free, which follows from its antisymmetry. Let us denote the non-vanishing off-diagonal elements of this matrix with alpha, kappa and tau. Now we can use this matrix form and we write the basis expansion of the derivative of the basis vectors as a matrix vector multiplication, where the matrix Aij is multiplied by a vector with the basis vectors as elements. For the given matrix elements, we can determine the result of this multiplication. In order to obtain the derivative of the first basis vector, we multiply the first row of the matrix with the vector formed from the basis vectors. This gives kappa times E2 plus alpha times E3. The derivative of the second basis vector is given by the multiplication of the second row of the matrix with the vector of basis vectors. Then we have minus kappa times E1 plus tau times E3. The last equation of the matrix multiplication is an expression of the derivative of the third basis vector, which is the multiplication of the third row of the matrix with the vector of basis vectors. This multiplication gives minus alpha times E1, minus tau times E2. Since the set of the basis vectors EI is an arbitrary orthonormal set, these three equations hold for any orthonormal set of vectors. Now let us consider the Frenet-Serret frame as a special case of the orthonormal sets, where the basis vector E1 is equal to the tangent t. The basis vector E2 is equal to the normal vector n. And the basis vector E3 is equal to the binormal vector b. Then the general equations can be written in the following special forms. The derivative of the tangent t is equal to kappa times the normal n, plus alpha times the binormal b. The derivative of the normal n is equal to minus kappa times the tangent t, plus tau times the binormal b. And the derivative of the binormal b is equal to minus alpha times the tangent t, minus tau times the normal n. But we also know that the normal vector n is defined as the normalized derivative of the tangent t. This means that the derivative of the tangent t is equal to its length times the normal vector n. By applying this expression, we can eliminate the derivative of the tangent t from the first equation. Then we see that the function alpha has to vanish, and the function kappa is just the length of the derivative of the tangent t. As a result, we can reduce these equations into a set of equations, which is called as the Frenet-Serret formulae. Namely, the first formula just tells that the derivative of the tangent t along a curve with respect to the arc length is equal to kappa times the normal vector n of the curve. The second Frenet-Serret formula expresses the derivative of the normal vector n along the curve with respect to the arc length, as minus kappa times the tangent t, plus tau times the binormal vector b. The third formula states that the derivative of the binormal vector b is simply minus tau times the normal vector n. We can also give the matrix form of the Frenet-Serret formula, where the left-hand side of the derivative of the column vector constructed from the vectors t, n and b, and the right-hand side is the multiplication of the antisymmetric matrix containing the two non-vanishing elements kappa and tau, with the column vector constructed from the frame vectors. Here the function kappa is defined as the length of the derivative of the tangent t and identified as the curvature of the curve at the parameter s. The function tau is equal to minus the dot product of the normal vector n and the derivative of the binormal vector b, which can be computed from the dot product of the third Frenet-Serret equation and the normal vector n. Here the function tau is called as the torsion of the curve at the parameter s. We can demonstrate that the geometric meaning of these functions are indeed the curvature and the torsion of the curve in a given point. We can examine what kind of planes are spanned by the Frenet-Serret frame at an arbitrary point on a curve, and what is their relation with the shape of the curve. But before doing that, we can check the consistency of the Frenet-Serret formulae with respect to the functions kappa and tau. We start with the multiplication of the second Frenet-Serret formula by the tangent t, which gives t times the derivative of the normal n in the left-hand side, and minus kappa times the dot product of t with itself, plus tau times the dot product of the t and the binormal b. Since t is a unit vector and perpendicular to b, we conclude from this equation that the function kappa is equal minus 1 times the dot product of t and the derivative of n. The normal vector n is perpendicular to the tangent t, therefore their scalar product vanishes. As a result, the derivative of their scalar product is also 0, for which we can apply the Leibniz rule. If we substitute this expression into the original equation, then we obtain the dot product of n and the derivative of t. Of course, we can remember that the tangent t is the first basis vector and the normal n is the second one in the Frenet-Serret frame, which means the first equality is minus e1 times the derivative of e2, that is, the element a12, and the second equality follows from the anti-symmetry of the matrix Aij. Thus, we have the dot product of n and the derivative of t, where n is just the normalized derivative of t. Since t times t is the square of the length of t, we obtain the length of the tangent t, which is the function kappa. Then we have a consistent result. We can also multiply the second Frenet-Serret formula by the binormal vector b. Here, b times n prime is equal to minus kappa times the dot product of b and t, plus tau times the dot product of b with itself. As b times t vanishes and b is a unit vector, we can write tau as the dot product of b and the derivative of n. We can use the anti-symmetry of the matrix Aij again, with b equal to E3 and n equal to E2. That gives minus n times b prime for the function tau, which is just its definition. Then we see that second Frenet-Serret formula gives a completely consistent result. Now we can introduce the concept of the osculating plane at a point P on a curve, as the limit of a series of planes passing through the point P, P', and P" on the curve, where the P' and P" are approaching P. Thus we have a curve Rs with an arbitrary point P, and the points P' and P" in the vicinity of P. These 3 points define a plane passing through these points, and this definition is unique, provided the curve is no a straight line. Then we can move the points P' and P" along the curve so that they are closer to the point P. Then the new points with the point P determine another plane. We can choose the new points P' and P" even closer to the point P, defining another plane with this new point set. We can continue this process with a series of point pairs P' and P", which are approaching the point P on the curve. As a result, we obtain a series of planes passing through the points P, P', and P". In the limiting case, the points P' and P" are getting infinitely close to the point P, and the limit of the series of planes is defined as the osculating plane. Actually, the osculating plane in a given point P of the curve can be determined by the Frenet-Serret frame in that point as well, since the plane is spanned by the tangent t and the normal n of the curve at the given point. This also means that the binormal vector b is the normal of the osculating plane in the point P. Based on the application of the Frenet-Serret frame, we can also define the normal plane of the curve in the point P, as the plane spanned by the normal n, and the binormal b. Then the normal vector of the normal plane is the tangent t of the curve in the point P. A third plane, called rectifying plane, can also be defined as the plane spanned by the tangent t and the binormal b at the point P. Then the normal vector of the rectifying plane is the normal n of the curve in the point P. In this table we can summarize the 3 planes, the set of vectors spanning them, and their normal vectors. If the order of the planes in the table is the osculating plane, the normal plane, and the rectifying plane, then we can just permute the 3 vectors in each row to get the corresponding vectors in the next row of the table. In fact, we only need the osculating plane to give the geometric interpretation of the curvature kappa and the torsion tau. Let us start with the geometric interpretation of the function kappa as the curvature of a spatial curve in a given point. We define kappa as the length of the derivative of the tangent t with respect to the arc length. We used curves parametrized with arc length, and proved that the derivative of the position vector r with respect to the curve parameter t is equal to the product of the derivative of r with respect to the arc length, and the derivative of the arc length s with respect to t. That is, r dot is equal to r prime times s dot, where we use the chain rule for the derivatives of composite functions. This rule can also be applied to the derivative of the tangent t, which tells us that t dot is equal to t prime times s dot. Then we can express the length of the t prime as the ratio of the length of t dot to s dot, where we suppose that the arc length s is a monotonic increasing function of the curve parameter t. In this figure, we can see a spatial curve with the position vector rs, pointing from the reference point O to the point P on the curve. We use the arc length s measured along the curve as the parameter of the curve. The tangent t of the curve at the point P depends on the arc length as well. Now, let us consider the point P' at the distance ds from the point P along the curve. Its position vector r and its tangent t are evaluated at the parameter s plus ds. We see that the direction and even the length of the tangent vectors can be different at the 2 points in the case of general spatial curves. If we translate the tangent from the point P to the point P', we can measure the angle phi between the tangent at P' and the translated vector. Let us denote the difference of these 2 vectors with the vector delta t. If the change ds in the arch length parameter is small, then the length of the difference vector delta t is also small. In this case, the squared length of the differential dt of the vector t can be approximated with the 1 of delta t, which is the scalar product of the difference ts plus ds, minus ts with itself. If we break up the brackets, we can write the square of the length as the sum of the squared lengths of the vectors ts plus ds, and ts, minus 2 times the dot product of the vectors ts plus ds and ts. Since the tangent t is defined as a unit vector, the sum of the first two terms in the right-hand side is equal to 2, and we can substitute the definition of the scalar product in the last term. Then the result is equal to the length of the vector ts plus ds times the length of the vector ts times cosine phi. The lengths of the vectors are unity again, and we obtain 2 times 1, minus cosine phi for the squared length of the vector dt. As we said, since ds is small, the angle phi is also tiny, which allows us to approximate cosine phi with its Taylor expansion in the first order. This gives 1 minus half phi squared. We can insert the approximation into the square length formula of dt and take its square root. The result is simply the magnitude of phi. If we multiply the first equation on the top with dt times s dot, where dt is the infinitesimal difference in the parameter t, then we can write the length of the vector dt as s dot times kappa times dt, since t dot is just the derivative of the tangent vector with respect to the curve parameter. Then we see that the length of dt reduces to the expression kappa times ds. From the last two equations we conclude that the magnitude of phi is equal to the function kappa times ds. Now we can divide this expression with ds, and as a result we can state that the curvature kappa measures the infinitesimal change in the direction of the unit tangent to the curve. That is, the function kappa is equal to the magnitude of the derivative of the angle phi with respect to the arc length s. Here we define the curvature radius rc as the inverse of the curvature kappa. Then, an infinitesimal change in the arc length s along the curve at a point P, is equal to the curvature radius of the curve at that point, times the infinitesimal change in the direction of the unit tangent vector to the curve. If we take the point P on the curve Rs with its tangent vector t and the normal vector n erected at P, then we can draw the osculating circle with the curvature radius rc and the center c of the circle in the direction of the normal vector n. The osculating circle is laying in the osculating plane spanned by the vectors t and n. The smaller the radius rc of the curve and the point P, the greater the curvature kappa of the curve is in that point. If the curve is a straight line, then the radius of the osculating circle becomes infinite in each point of the line, that is, the curvature is 0 along the line. This is the geometric interpretation of the function kappa. We can also provide a geometric interpretation of the function tau as the torsion of the spatial curves. It goes as follows. The torsion is given by the dot product of the normal n and the derivative of the binormal b. By definition of the scalar product, this expression measures the infinitesimal change in the direction of the binormal relative to the normal of the curve. Let us examine this definition in a greater detail. Here we can see the Frenet-Serret frame at the point P on the curve Rs. When we move along the curve from the point P to the point P', the frame also moves along the curve. In the case of a general curve, the directions of the frame vectors will change with respect to those of the frame vectors at the original position. Now we can translate the binormal b form the point P to P', and take the difference vector delta b between the translated vector and b. If we translate the vector delta b into the point P', we can just project it onto the normal n, and denote the length of this projection with tau. If the function tau vanishes, then the third Frenet-Serret formula implies that the derivative of the binormal vector b vanishes in the direction of normal vector as well. This is represented by the vanishing projection of the difference vector delta b onto the normal direction in the figure. As a result, we see that the binormal b does not depend on the arc length but it is constant along the curve. If we denote the arc length with s0 at the point P and with s at the point P', we can define the function f depending on s by the dot product of the vector pointing from P to P' and the binormal vector. Here the vector P' is simply the difference of the position vectors r with the arc length parameter s and s0. It follows from that definition that the function at s0 vanishes, and the derivative of f is equal to r' times b, since r s0 times b is a constant. By using the definition of the tangent, we can substitute the vector r' with the tangent t, which is perpendicular to the vector b. Then we obtain that the derivative of f vanishes. That is, the function f is constant. But we already know that the function f at s0 is 0, which means that the function f is identically 0. As a result, the vector P' is perpendicular to the vector b for any arc length parameter s. Then our main conclusion is that the curve Rs is a plane curve lying in the osculating plane. Remember that the binormal vector b is the normal of the osculating plane. Now we can check what the first two Frenet-Serret formulae give, if the function tau vanishes. The first formula states that the derivative of the tangent is equal to kappa times the normal vector n, that is, it does not depend on tau. Whereas the second formula reduces to a simple expression, stating that the derivative of the normal n is equal minus kappa times the tangent t. These two equations tell us that the tangent t evolves in the direction of n, and the normal vector n evolves in the direction of t as we are moving along the curve. Since the tangent t and the normal n are spanning the osculating plane, this evolution equations also show that the curve remains in the osculating plane determined in the original point P at the arc length parameter S0. Then we demonstrated that the torsion tau measures the rate which the curve lifts or twists up off the osculating plane for an infinitesimal change in the arc length parameter along the curve. By introducing the Frenet-Serret frame, we can describe the velocity and the acceleration of a body moving along an arbitrary spatial curve in a convenient way. We already determined the first and second order derivatives of the position vector are with respect to the time, that is with respect to the parameter t of the curve. Its first order derivative is the derivative of the arc length s with respect to the time, multiplied by the derivative of the position vector r with respect to the arc length. That is, r dot is equal to s dot times r prime. The second order derivative of the position vector, that is r double dot is equal to s dot squared times r double prime, plus s double dot times r prime. The magnitude of the velocity is the speed, which is the time derivative of the arc length, that is the path covered in a given time. Since the speed v is equal to s dot, and the tangent t is defined as r prime, we can write the velocity vector as the speed times the tangent vector. This result shows that the velocity vector of the body points into the direction of the tangent to the path of the moving body, as we expected. The tangential component at of the acceleration is the time derivative of the speed, which is equal to the second order time derivative of the arc length, that is s double dot. The vector r double prime is simply equal to t prime. Then the acceleration vector can be written as the tangent t multiplied by the tangential component at of the acceleration, plus the speed v squared times the derivative of the tangent t with respect to the arc length. Now we apply the first Frenet-Serret formula stating that the derivative of the tangent t with respect to the arc length is equal to the curvature times the normal vector n. Then we can write the acceleration vector as the tangential component of the acceleration times the tangent t, plus the square of the speed v times the curvature kappa multiplied by the normal vector n. Here the second term is the square of the speed divided by the curvature radius, times the normal vector n. Then the velocity and the acceleration in the Frenet-Serret frame at the point P on the curve Rs are the following. The tangential component of the velocity is equal to the time derivative of the arc length, and it has no normal and binormal components. The tangential component of the acceleration is the time derivative of the speed, or the second order time derivative of the arc length. The normal components of the acceleration is equal to the ratio of the speed squared to the curvature radius of the path measured at the position of the body. The binormal component of the acceleration vanishes. In the figure we can see the curve Rs with the Frenet-Serret frame at the point P, and the osculating circle with the radius Rc. These equations restate that the velocity vector v points into the tangential direction of the curve at the point P. At the same time, there is a tangential component of the acceleration, and it only depends on the change in the speed, while the shape of the trajectory of the moving body is irrelevant. However, the acceleration has a normal component, which depends on both the speed of the body, and the shape of the curve representing the path of the moving body. This means if a body is moving along a curved path, then its acceleration vector will not vanish, even if the body moves with a constant speed. In the end of this presentation on the basic concepts of kinematics, let us summarize its main conclusions. First of all, we saw that motion is relative, and it is always described with respect to a frame of reference. We need to attach some coordinate system to the frame of reference, so that we can carry out a quantitative analysis of the motion. We also need to introduce idealized models for the bodies when we study their motion. Such models are the point mass, systems of point masses, and elastic and rigid bodies. We also have to define the basic kinematic quantities, such as the position vector, the velocity, and the acceleration of the moving bodies. By applying the coordinate systems, we can have a numerical description of the kinematic quantities in terms of the coordinates of the moving bodies. The numerical form of the kinematic quantities is expressed as a set of vector functions of time, and called equations of motion of a given moving body. We can construct Frenet-Serret frames from the geometric properties of the general space curves along which bodies move, and attach the frame to the bodies moving along these curves. Then the kinematic quantities of the moving body can also be given in this frame, which provides an efficient way for us to describe the most general forms of motion in mechanics.